Hello, everyone. Uh, I'd be presenting our work on jointly learning to align and translate with transformer models. This work was done with my collaborators Stefan, Uday, and Matthias at Apple. So the goal of this work is to learn a neural machine translation transformer-based model that does not compromise on translation quality and can produce very high quality word alignments. So most of you must already be familiar with the translation task, and I'll describe the alignment task briefly. So in the word alignment task, we assume that we are given the source and the translation. And what we need to do is find a mapping between the source words and the words in the translation. And the goal is to map every source word to the set of target words that sort of originate or correspond to it. So in this example, we can see a source sentence in English in the left and its translation in the right, and the blue arrows indicate one such alignment mapping. So the question arises why we actually need these alignments. And there are several possible use cases of word alignments. One of them could be to transfer annotations or metadata from the source sentence to its translation. So whenever we are sort of translating content with rich formatting, various stylizations or hyperlinks, we need to transfer these annotations to the correct places in the translation. And if we have a word alignment mapping, then we can do this very easily. And also another very important use case for alignments is to model source side coverage. And a lot of NMT models sometimes can perform under translation. For example, in this case, like the word downstairs has important information but is actually missed in the translation. And this problem can be detected by the missing alignment link for the word downstairs on the source side. So how do people do alignment? Right now, the statistical alignment toolkits are the go-to solution for computing alignments. Two of the most popular toolkits are Giza and FastAlign. Giza is a very robust method, gives a very competitive alignment accuracy, but is slow to train. FastAlign, on the other hand, is much faster, but compromises a little bit on the alignment quality. One major drawback of these methods is that these are batch trained. This means that if you want alignments for source translation pairs, you have to feed all such pairs during training time to these models. And if you want to infer alignment information for new source target pairs, the inference is not straightforward. So why not just learn a neural machine translation model that also gives you very good alignments? And the first thing that comes to mind is why not use the encoder-decoder attention to extract these alignments. But in the past few years, there has been sufficient evidence now that the attention mechanism models a lot more than just word alignments. And if we just interpret these attention probabilities as word alignments, then you can get a lot of off-by-one errors, as shown in the picture in the bottom right. So we construct a simple baseline to extract alignments from the attention mechanism of a transformer model. So since the transformer model has a multi-layered, multi-headed attention, what we do is we simply pick one layer, select one layer of this transformer model, and average the attention probabilities over all the heads, and then use this layer averaged attention probabilities to extract alignments. So we could train a source to target translation model and then decode the target sentence. And while decoding every target word, we can look at the layer averaged attention probabilities over the source and pick the maximal one and align the target word to that. So in such a way, we can, for every target word, get an alignment to a source word. We can do this process, exact same process other way around as well, where we train a reverse direction translation model and decode the source sentence, and while decoding the source sentence, get an alignment for every source word to a particular target word. So a very common practice in computing alignments is symmetrization, where we take the set of alignments from the forward and the reverse direction and sort of symmetrize them. the major component of such symmetrization is usually intersection. And the intersection retains only those alignment links which are agreed upon by both the directions, and it thus filters out a lot of noisy alignments. So we end up with more precise but fewer word alignments. Okay, so how does this simple layer average baseline work, and how does its performance vary as we vary the layer number from which we extract these alignments? So we run experiments on 3 language pairs, and across 3 language pairs, we find a very similar trend. In the graph shown below, the x-axis represents the layer number from which we use to average the attention probabilities, 1 being the bottommost one. And on the y-axis is the alignment error rate, which like lower is better. And we observe that the bottom layers are not very good at modeling word alignments. They're probably just focusing more on self-attention to compute good representations for the target sentence first. But as we go higher up, we see that across all the 3 language pairs, the penultimate layer is the one that's best at modeling word alignments. So we just choose the penultimate layer and average the attention weights that we get in this layer to extract alignments in the layer average baseline. So how does this naive method like sort of compare to the state-of-the-art statistical alignment models? So actually it performs pretty bad. So here you can see that symmetrization reduces the alignment error rate a bit, but there's still a very large gap between the layer average baseline and the GISA++ method. So we dig a little bit deeper into what's going on by evaluating the symmetrized case for using different evaluation metrics. So we look at AER and precision and recall. So AER is like a combined error metric that's a combination of precision and recall. And we make a very interesting observation that the layer average baseline actually produces very precise alignments. Like the alignments it produces are of as high quality as GISA++. It's just that it predicts a very few number of alignment links. That's why the recall of this method is much lower than GISA++. So now the idea is, can we take these very precise but very sparse alignment links and using these like supervise one head of the transformer model and just supervise it to model word alignments. So the hope is that if we supervise explicitly one attention head, then it can extrapolate this alignment behavior to produce dense links. So that's exactly what we do in the next step. In the next step, we train another NMT model with a multitask objective. So in the objective shown below, the first part is the standard negative log likelihood, which is the translation loss, and we add an extra alignment loss by selecting a head. And we force the attention probabilities of that head to be close to the alignments that we get from the layer average baseline. So suppose we get an alignment from the layer average baseline. In this case, the target word is aligned to tell. We convert it into a one-hot distribution and then minimize the KL divergence between the attention distribution and this one-hot alignment distribution. And now we want to ask these questions about this method. First of all, how good is the alignment accuracy of this method? How does it compare to the layer average baseline on which we actually train, using which we actually train this? How well is it compared to GISA++ and the other baseline methods which use NMT models to extract alignment? And the second, an important question is, does this multitask objective somehow hurt the translation performance in a state-of-the-art translation setup in a high-resource scenario with a big transformer, big network? So we'll answer the first set of questions first. So for a fair comparison with earlier baseline method proposed by Zenkel, we follow their exact same dataset setup, and we compare 3 language pairs. The dataset statistics are shown in the table below. And here are the results of the method. We observe exactly the same trend across all the 3 language pairs. So if you look at English-French, for example, the gray bar, which corresponds to multitask, improves a lot upon the layer average baseline. but it still isn't able to outperform Zenkel et al.'s method, and also is much worse than GZA++. So in order to improve our multitask model, we introduce full context alignment training. So in the self-attention component of the decoder, we mask out the future tokens. This means that the token representation is only allowed to attend to the token representations of the past tokens and not the future. And this is done so that the model cannot trivially learn to copy the target token. However, this conditioning on just the past is limiting for the alignment task, because for alignment, we assume that we already have access to the whole source and translation sentence. So in order to resolve this discrepancy, we compute two sets of representations simultaneously. One is the H set of representations that's shown here, which is computed in a normal way with only the past context. We compute using the same shared parameters another set of representations G, which removes this masking and allows attending to the representations of all the tokens. Now we compute these both set of representations and reparameterize the two parts of our objective to be conditioned on different amounts of context. So the first, the standard negative log likelihood translation loss, is computed using the H set of embeddings, just on the past context, and the alignment loss is computed based on the G set of representations, which can take advantage of the full context. And here are the results after we incorporate full context alignment training. That is shown by the orange bar, and it improves upon the gray bar, which is just the multitask training, by quite a lot. And now we are able to outperform the prior methods by Zenkel et al., and come very close to GZA++. In fact, on Romanian English, this method beats GZA++, but comes very close on German English and English French. So far, what we've been doing is that we were training our model based on alignments obtained from layer average baseline. So what we wanted to try out is, would it help if we train starting from better alignments? Would it help if we train on GZA++ alignments, let's say? Will it be able to outperform GZA++ using some knowledge from the translation task? So here are the results if we do that. The red bar represents the alignment performance when we train our model using GZA++ alignments. And now it's able to significantly outperform all the other baselines as well as GZA++. Now we move on to the next question. Does it actually hurt the performance of a state-of-the-art translation setup, the translation performance? So for this, we have a separate dataset setup here where we have 5.2 million examples from WMT18. For evaluating translation quality, we use News Test 13. Alignment quality is evaluated on the same test set as earlier. And we use the transformer BIG for this setup. And we see a very similar trend in terms of alignment performance, where our best method, the orange bar, GZA++ supervised, is able to outperform all the other methods in terms of alignment error rate. And here are the numbers on translation performance. So the layer average baseline in the first row just represents a regular NMT model training. And if you look at the rows multitask, full context, and GZA++ supervised, then they are able to achieve more or less the same translation performance as layer average baseline. So to summarize our work, the take-home message is that we can have one NMT model that can learn very good alignments and translation by having a multitask objective. And the alignment loss in this case would be supervising one attention head to be close to alignments obtained from statistical alignment toolkits or layer average baseline. For computing the translation loss, we can just use the past target sentence context. And for computing alignment loss, we can use the full target sentence context. We observe no degradation in blue, but we are able to outperform all other baselines in terms of alignment accuracy. And this method, our models are implemented in FAIRSEEK, and you can get started with an example in the link shown below. Thank you.
Thanks. thanks for the talk. Did you filter length? Did you have what's your max seq length? Maximum sequence length?
So
especially for, I mean, let's just say for all tasks, but especially for the German-English or English-German.
Yes, I think for fair comparison against translation performance for the second setup, we use the exact same data pre-processing as a strong baseline work by Edenov et al. That's the paper understanding back translation at scale. So we exactly use their setup. And I believe that there's a length filtering on 100 words there. The maximum sequence length is 100.
Okay, thanks.
For the layer average baseline, it was where you were seeing low recall but high precision. I was wondering, do you just extract like one-to-one alignment points, or I mean, you could add more alignment points from the target to the source?
So if we the reason that it's low recall is because a lot of these alignment points are filtered out when we do the symmetrization. And that is something that we found very important because the quality, the AER precision and recall of the individual alignments is very noisy. But when we do the intersection, it just keeps the good alignments. You can see from this figure as well, if you compare the two charts, then there are a lot of off by one errors on one side. So if you take the intersection of both of these, you'll end up in getting very few alignment links, but the ones you get will be quite accurate. And thus we used only those for training.
Okay, thanks.
Okay, last question. So there is a... Okay, that's it.
I had a question regarding the units you're using. Are you using some kind of BPU units anywhere in your system? And if so, how do you reconcile the alignments of various subparts at the end to get word alignments?
Yeah, so in our experiments, we used BPE, around 32,000 BPE merge operations. And to get word alignments from subword level alignments, we use a naive method that a source word is aligned to a target word if any of the BPE splits of the source word is aligned to any of the BPE splits of the target word. That's a simple rule that we used.
But if you do so, you can get inconsistent alignment with, I don't know, subwords attending to various parts of the sentence, for instance, and having very confusing alignments. Don't you,
yeah,
do you encounter these cases, or do you anything to solve them?
We were actually wondering if this naive approach could be harmful, but in practice we saw that even the alignments of the broken subwords, let's say we have a long proper noun, it's broken into 3 or 4 subwords, even the alignments of each of the subwords was pretty accurate. So we didn't see any cases where we are losing out because of subword to word level alignment conversion.
Okay, so that's the end of this session. Thanks to the speaker again. So let's thanks to all the speakers.